hints on how to go about the problems, trends that you should be able to recognize. Remember that this is a language of continuum mechanics we are still looking at. So I'm going to refer you to the notes where, so I'm just going to have a very short kind of briefing or lecture before we go into the main tutorial. There's a very important table for you to understand how to go about the tutorial questions. And that has to do with the Gateau and Frechet relationship. The Gateau differential, how is related to the Frechet derivatives. So if you go to that part of the notes, I will give you some time to open it. Is either you get to the slides or you have the notes. I already have I have a notebook that has the summary of the notes. So I guess that while you were reading chapter 3, you should be able to locate where that is. So I'll give you a minute. Once you see it, where we have the gradient of Frechet derivatives. And we talked about the relationship between the Gateau differential and the Frechet derivative. If you have seen that part of the notes, please just say seen before I go ahead, because it's important you open to it before we move on. And see that some of us have seen it. Good. So just in summary, is just to label what we have on the board. The Gateau differential is like the general form of our, when we're doing calculus in high school, when we do our dy dx, everything that we dealt with at that level were scalars. But when we now take into consideration tensors, vectors, the general form that we are supposed to write those differential is what we have as our Gateau differential. So if we have scalar valued functions, vector valued functions, tensor valued functions, we can find their differential. So the Gateau differential is just a build-up on what we regularly know in high school. But what we did then only covered scalars. But remember that when we are doing design and talking about the space that we are in, we are going to be dealing with vectors and you are going to be dealing with tensors. And you must be able to carry out a differentiation of those kind of functions. And that's where the Gateau differential comes in. Now, there is a connection between the Gateau differential and the Frechet derivative. What we actually know as the Frechet derivative for some of us, it actually came about when we were talking about, the issues of partial differentiation and things like that. But the general form is the Frechet derivative. So when we are talking about the derivative, it has a connection with the Gateau differential. And the connection is what you can see on the whiteboard. So you will see in that note a scalar, vector, or tensor value domain, because the domain that we are going to be operating in can either be a scalar, that's the domain of real numbers, can be vectors, the domain of our Euclidean space, or can be a tensor domain, which actually is a linear transformation. So a scalar, vector, or tensor value domain is said to be Frechet differentiable if a subdomain exists in which we can find this grad such that we have this relationship that I've written on the whiteboard. This equation defines the gradient of a function in terms of its operation on the domain object, okay? So there is a table that tells us if our grad is a scalar, if our argument is a scalar, the kind of product we can have and the kind of function. So I'm going to put that table on the board and I'm going to explain it one by one so that you can understand. So if you look at that table, you have grad, grad f of x, which is what you have here. That's the first term you can see in that expression above. We have the argument. Your argument in the expression above is h bar, but it could be anything. It could be a scalar, it could be a vector, it could be a tensor. We have the product. You will see that in the expression above, I put a very big round dot. So that big round dot is not a scalar, it's not a scalar dot product. It can be scalar multiplication, it can be vector cross, it can be a dyad product, it can be a dot product. So I just use that big dot to represent the product between the two terms that we have. Depending on what the terms are, that is what is going to define what the product is, okay? So we have the product, we have the function itself, and we now have the Gateau-Frechet relationship. So that's the table. Because we are going to need the understanding here in some of the tutorial questions. So are we all seeing the table where we are? I mean, in our in the notes that you have, do you have it? Do you have that table so that I can go ahead? Do you have that table? Just waiting for you to tell me you've seen the table in your own notes. So that as I pick it one by one, you can follow me. Okay. And all I can see you. I'm just waiting for I think we have 6 people here already. Okay, Mujiradi, I can see you. Okay, so we go ahead. So if grad f of x is a scalar and the argument is a scalar, the product that we have is multiplied, the normal scalar multiplication. Means that function is going to be a scalar. And using the expression that you can see on the board, it means that what we have is going to be dfx is equal to dfx, finding that derivative with respect to x dx. So you will see that I did not put any dot or anything. It's like it's a normal multiplication because what we have there is a scalar. So let's look at this one by one. You can actually walk backwards. For example, if they give you this, and of course, you know the argument, you can get this. So this table is just telling you, it doesn't really go in this order. You will see that from the tutorial questions, what we are asked to find most of the time is this. when you are given this Gateau differential, and you also have the arguments. And from what you have, you can know the kind of product you have. Because if your grad, f of x is a scalar, your argument is a scalar, the function you are given is a scalar, then the product that you will have here can only be a scalar multiplication. It cannot be a dot product because you can't carry out a dot product between a scalar and a scalar. It cannot be a dyad product. It cannot be a vector cross. It cannot be a contraction. All you will have is a scalar product. So you will see that if, for example, I'm giving the Gateau differential and I know what the argument is, I know what domain we are operating in, then what it means is that I can determine the product and I can find the Frechet derivative based on this relationship that I have above. Because we are very few in this class, I can allow us on mute to ask a question. The first row of this this table, is it clear? Is the explanation clear? Because I'm going to go to a next one when we have something different. Is this clear for now? We are given the Gateau differential. We know that the function that we have in that Gateau differential is a scalar function. Is a scalar valued function. We know that the argument that we are given is a scalar. We are asked to find the Frechet derivative. So you can see I'm working backwards now. Based on the relationship in the last column, I can actually get the Frechet derivative, which is what I put the double line under. And I can also know the kind of products that will be between that derivative and the argument. Please, is this clear? Or do we have a question? Should I move on to the next one, maybe to make it clearer? Okay, Enola, thank you. Okay, okay. So I'm hoping that the others are following. Because we are few, I'm just ensuring that we have a minimum of 2 people respond to me before I move on. Now, if we have what we have here, if what we have here is a vector, and the argument is a vector, and the function is a scalar, what kind of product would we have based on the relationship above? The derivative is a vector. The argument is a vector. The function is a scalar. What kind of product would we have? It's going to be a scalar product or a dot product. So what will be here will be a dot product. I'm going to write what is going to be in the last column so that we can see. So of course, our Gateau differential here will be D. Remember that we said that the function is a scalar. So I'm going to represent it with this. So this represents the function. I know that the argument is a vector. So I'm going to have this argument here, which is a vector. So for you to get a Frechet derivative that is a vector, in this case, is going to be a grad, because the grad of a scalar function is a vector. So that means grad of phi x. Since our you will see that your Gateau differential there is a scalar, because look at that function phi is a scalar. So for you to get a Gateau differential that is a scalar, then it means that it has to be a dot product between your Fertré derivative and the argument. So the way I was able to get the product was to actually look at the Gateau differential. I saw that what I have there is a scalar valued function. Okay, but I've been given that the derivative is a vector. So, and I know that the grad of a scalar valued function is a vector. And I've been told that the argument is a vector. So based on the relationship I wrote on the board, the first relationship I wrote, I know that the only way I can get a Gateau differential that is a scalar value function is to have a dot product between a vector and a vector. A vector and a vector. Now, let me go to the next one. So it means that if I'm given the Gateau differential and I know the kind of argument that I have, I can actually find the derivative. I can also know the kind of product that would exist between the derivative and the argument. So I can find those missing, I can fill in the blanks by those information. So I'll do a third one because you have the other ones. From what I've said, I think you can follow through to the rest. But let me do the third one on the table. If my derivative is a tensor and my argument is a tensor, and my function is a scalar, you will see that what I will have as my product to be a scalar product. And you know that for the scalar product of two tensors, you use that double dot. So if I write the last part of this, so what I'm writing is for this one here. My Gateau differential, I've been told that the function is a scalar. I've been told that the argument is a tensor. I've been told that the derivative is also a tensor. So if I'm doing d of a scalar with respect to a tensor, oh, there's no space here. Let me just write it somewhere. If I'm doing d of a scalar function with a tensor argument with respect to a tensor, this will give me a tensor. This will give me a tensor. And I've been told also that the argument is a tensor. And I know that what I'm going to get for my Gateau differential is a scalar. So this f here is a scalar valued function. So the product between a tensor and a tensor that will give me a scalar is a scalar product. And if you check the other tables, you will see that when you have a derivative that is a tensor, an argument that is a vector, and your function that is a vector. So what you would have there is that you have the grad of your tensor multiplied by a vector. The only kind of product that can exist between a tensor and a vector is that contraction. It's like the linear transformation of a vector to a vector. Is that contraction. And it goes on and on and on like that. So from your rules of the kind of products that exist within your domains, that previous knowledge is what you are going to use here. That previous knowledge is what you are going to use here. And what I'm going to do right now is I'm going to use an example from the tutorial questions to make this very clear to those of us that are still struggling to understand what is going on here. Should I go ahead or does anyone have a question? Should I go ahead or does anyone have a question? So this table is actually what you need for, I think, the first part of the tutorial questions that asked you to do some to show that the derivative of the trace of a tensor is equal to something and all that. You are going to use this Gato-Freche relationship to get your results. Should I go on or does anyone have a question? Maybe you want them to unmute you or I should go ahead. Okay. Okay. And Nola says I should go on. Like I usually wait for a minimum of 2 people to respond. Bolaji, Fisayo, Kenneth, Mohammed, Mojirade, and Enola have been the ones responding. Is it that I want to hear from either of those that I called now? Okay, Mohammed says I should go on. Okay, so just to be sure that we are all on the same page. So let's use this this relationship to solve some of our tutorial questions. So the first question that I'm going to solve is, given any scalar k greater than 0 for a scalar valued tensor function. So the first question, we have a scalar valued tensor function. And the scalar valued tensor function is the trace of S. If you find the trace of S, you see that this trace, which is the function we're looking at, the trace is a scalar. The argument that we have here is a tensor. So that's why this can be called a scalar valued tensor function. Okay. So if we are given a scalar valued tensor function and we are told that when we find that derivative, we have the identity tensor. We are asked to show, oh, I think this is an example in the note, but let me see if we say I'm working with tutorial 3, the slide that is called tutorial 3. So let me see if I can get I know that the question that was solved for when k is equal to 2, but I want to solve for when k equal to 1. Moderator, just give me a minute. Let me put my computer back on to get that question. I already have a note where I broke those questions down into bits. So I had my own numbers. But let me just give me a minute. Let me get back to the slides and see. But I'm very sure that this is within the notes. It might not be within the tutorial question. If anyone has seen it, the one I'm solving, in this case, k is greater than, our k here is 1. The one that we have in tutorial 3, I think we use k is equal to 2 and k equal to 3. So I wanted to start from a simple one before I go to a complex one. So I'm using tutorial 3 slides. Let me see if this one is there. Okay, so if you go to tutorial 3 slides, slide 11. Slide 11. that said, show that DDS trace of SK is equal to K into SK minus 1T. Have we seen it? There's a particular slide that is a tutorial question slide, 70 pages. That's the slide I'm using. Please quickly let me know if you've been able to locate that slide. So for the one I'm solving for K equal to 1. When K equal to 1, we just have the trace of S. Then I will do K equal to 2 and K equal to 3. Okay. Enola, thank you. You've seen it. So you will see that in that slide, it says K equal to 1 and 2 are already provided in the text. So it means it was already solved, maybe within the notes, but I want us to go through it. Mojira, have you seen it? Mohammed, Bolaji, Duka, Fisayo, Kenneth. Have you seen what I'm looking at? So I'm waiting for everyone. Oh, no. Okay, let me direct you. Everybody, this is important. I will want you to see it. This is important. It's important that you see it, because when you are going through those tutorial slides, it's good that as you are making notes here, you can connect it with the material you are using. So everyone, if you go to the website, the web page, the one for MEG 805, you will see that there are a couple of materials under chapter 3 there. There are a couple of materials under chapter 3 there. Maybe what I should do, you know what, let me connect the place. This is very important for me. I need everybody to be able to locate where the material I'm using is. So just give me a minute. Let me join with my laptop that has where I open the web page. Let me stop share here. Okay, so I'm purposely sharing this screen. I'll get back to my whiteboard so that everybody can. Let me go back. So this is our MEG 805 page. So if you go there, you will see that here you have tensor analysis. Just drop that plus sign. Then you will see tutorial 3 and click on it. When you click on tutorial 3, you will see that there's a video already from previous sets that I have, but there's also a material there. And that material also has a PDF here. Okay. So just get that PDF. And that's what I'm using for today, 70 pages. Only Mojira Day is communicating with me. That's why I'm referring to her. But hopefully all of us. So you just go to slide 11. So this is slide 11. So the first one I'm solving, and first of all, even though they said K equal to 1 and 2 has been given the notes, but I want to start from that simple example when K equal to 1 to establish the Gateau-Freche relationship. Okay, have we got it now? I know Mujirade would have got it. I want to hear also from Mohammed. Enola already has it. Kenneth, Fisayo, Duka, Godwin. We are just starting the real tutorials now, so it will be good for all of us to be on the same page. So just let me know that you already have it. I want to stop sharing this particular screen so that I can go back to my whiteboard. Hey, everyone, let me know what is going on at your end there. Don't just keep quiet, please. This tutorial is meant for you. I'm not supposed to be speaking to myself. Okay, Mohammed said we search for it. Okay, Kenneth has it. Do we have any other person that has it? Fisayo, you've never used the web page before. Okay. I'm really, really very surprised. Okay, if you have you located MEG 805 before on the web page? So why did you now say you can't find it now? I just showed you the process now. This is our MEG 805 page. Now I'm talking to Fisayo. Am I correct? Is this our page? Is this where you are? I just have 1 more minute to do this. I want to get as many people on board as possible. And just click on it now. Once you click on it, it takes you to the materials that we have here. Scroll down. Tensor analysis. Okay, Mujirade has it. Tensor analysis, drop down that plus sign. Besides, I hope all these efforts are making just to ensure that you get this thing, or you are following. If you are not on your laptop and you are not doing this, just let me know so that we don't drop it down. And tutorial 3 is just here. Tutorial 3 is just here. Click on it. Once you click on it, you see that there's a video. Of course, you can see I'm the one that was from the past. Okay. And you will see a material here. This is chapter 3, the full text. This is the tutorial slides, PDF. So that you don't need to burn your data. Just click on that tutorial slide and you are here. Okay, fantastic. So we are all here. So I'll stop share here. I think I got a couple of people with me now. All right, so let me go back. Okay, good. I know I'm glad you watched the video. I hope it was very useful. I actually wanted to say you guys should watch the video and there was no need for tutorials, but anyways, we are here right now. So back to my whiteboard. Okay, great. So back to my whiteboard. We are dealing with slide 11. Now I've joined with 3 systems. I'm just hoping that this will not affect my network. But let me just still keep this on. So slide 11, if you are there, that question over there says that we should show that trace of DDS, trace of S to K is K SK minus 1 transpose. So the first one we are looking at is for K equal to 1. So for K equal to 1, and everybody, this that is written on the board, is it the Frechet derivative, the Gateau differential, or what? What is it? This expression that we are giving, is it for the derivative? Is it for the Gateau differential, or what? What is it? You need to recognize what it is for us to use that table. Anyone? Gateau, Frechet, which is it? You can also check your table if you want to identify it. there's a way we write differential derivative, and there's a way we write the Gateau differential. So that's just what you need to recognize to know which is which. I'm waiting. Is a Freche derivative. Very good, Mujirade. That's very correct. So, first of all, for what I was trying to solve, you need to first of all see that no, this is not correct. It's identity. Sorry. I'm supposed to show that this is our identity tensor. So first of all, our Gateau differential, remember they said a scalar valued tensor function. Let's assume that we don't know what that function is. So I'll just represent it as that small letter f. That small letter f represents my scalar valued function, but it has tensor arguments. And in this case, the tensor is S. So if I'm going to write the Gateau differential, this is what it will look like. And from your notes, this Gateau differential can also be written like this. Have we seen this in our notes while we're reading this chapter? That your Gateau differential can be written as this. So while you were reading this chapter, you know you're supposed to have read the chapter before we come in today. Anyway, your Gateau differential can be written as this. And of course, our function in this case is the trace. What we are given in the question, we have already been told what the function is the trace. So what we are actually given is that this is okay. Now, if we are carrying out a differential of this trace as x, as alpha goes to 0, first of all, we are doing d the alpha. If we are doing d the alpha, you will see that what will be left here will be the s. Your s will go out because there is no alpha in that first term. So your derivative will give you the s. Okay, but you cannot find the trace of just one tensor. So it means that this answer, the answer to this differential that you carry out, is going to be trace of your identity tensor and the S. We first of all did the alpha of what we have here. The only thing that has alpha here is this term. If you carry out that differential, what we have is ds, okay? And since we have a trace as a function, you remember that your trace is going to be between two tensors. And you know that your identity tensor, the product of your identity tensor and your ds is still ds. So you can write it in this form. And of course, this you can also rewrite as, remember that you can write your trace also in this form. Okay? You can also write your trace in this form. And you know that for you to get an identity tensor, you see that this is the same as saying you had a df of s with respect to ds. This has also been proved somewhere in the notes. So you see that this identity tensor is this. Your ds is still your ds. Okay? So from here, you can see that your the trace, the DDS of the trace of your tensor S is actually an identity tensor. The DDS of the trace of your S is actually your identity tensor. Remember that this is the first thing we wanted to show. And using the Gateau-Frechet relationship, we have been able to show that. So from here, you will see this our F. Remember that this F here is a scalar valued function. And remember that our F in this case is our trace. So we are able to see that DDS of the trace of S is the identity tensor. Any question on this? Any step that I did here that wasn't clear to you? I'm ready to go back, because there are some other things that we need to do, which builds on this. This is the simplest, kind of the simplest example I can use to show that relationship. So if you understand this, we can build on it. Any question? If you want to be unmuted, just raise your hands and the admin will mute you. Okay, I should go back. Okay. So Duka, if you go to your table, so everyone please allow me to take this off. If you go to the table we started with, except you came in late, on that table, if your grad, your Frechet derivative, why are we differentiating with alpha and not S? Mojirade, by now, if you read the notes, you would be able to answer that question. What you are asking me to do is to go back to the notes. I'll refer you to the part of the notes you can read to see that. Where we see differentiation, vector and tensor arguments. Differentiation, vector and tensor arguments. There's a full note that tells you how the Gateau differential can also be rewritten as d alpha. Modirade, did you get that? That is it's part of the chapter 3 notes that I should have read before today. So I'm just building on that. So that topic is differentiation. When we say differentiation, vector and tensor arguments. So there is a theorem that was written there, and we wrote for alpha in the real space, we can write this as this. So that is before we started looking at the gradient and Frechet derivative. So that comes before this. So just go check it out and go through it. But there's a proof already that shows that we can write a Gateau differential in that way. So I'm coming back now to Duka. So we have this table, we have our arguments, we have our product, we have our function, and we have our Gateau-Frechet relationship. So if you check that table, for the case we are dealing with, we have been told that our derivative is a tensor. From the question, is a tensor. Let's leave the argument for now. We have been told that the function is a scalar. And we have been told that, let me just write what we have here. We have DDS trace of S. So the trace that we have here is a scalar. That's the function. The argument is a tensor. That's the S we have there. The Frechet derivative, as you can see here, the trace of S is a scalar, but we are differentiating with respect to a tensor. So that makes this whole thing a tensor. That's why our Frechet derivative here is a tensor. Now, our Gateau differential, if your function is a scalar, your Frechet derivative is a scalar, your argument is a tensor, based on the Gateau-Frechet relationship, your product here will be a scalar product. So if you look at that table, if you came in late, oh, there's nothing I can do, you have to watch this recording. So if you look at that table, you will see that what we have there is the Gateau differential of a scalar function with tensor arguments, written this way, is equal to dft dt scalar product dt. That's why I told us that we needed to understand this table. So if they give you a question, you have to know which of the cases on that table is being dealt with. And for the question we are looking at, this is what we are looking for. This is what we are dealing with. Okay, so that's the first thing. And I hope Duka is following. The next thing is to write the Gateau differential. Okay, of that function. So the Gateau differential of the function is and this Gateau differential can also be written as d the alpha what I've written right now on the whiteboard is our Gateau differential. Now, because the function that we are giving, we know it, the function is trace. So what it means that specifically for this question, what we are writing is this. So what we want to do now is to find this differential. So d the alpha of what we have is going to be trace of I ds. Because the only term with alpha here is alpha ds. So when you do that differentiation, what you have left is ds. Okay, what you have there is ds with your trace. And of course, you know that the identity tensor, the product of the composition of your identity tensor and ds is still ds. Okay, and this can also be written. Remember that you can write your trace like this. Please, are we clear to these points that I've written now? The question Modira asked was based on this. There's already in our notes in that chapter 3. This was already explained there. That's why I referred that to that. But I want you all to know that you can write your Gateau differential in this form, and you will see it occurring regularly. So just recognize that for now. But the explanation behind it is already in the notes. Are we clear up to this point? Should I move on? Okay, good. Now let's look at our table. Can we see this? So, but in our case, we have our Gateau differential. We have our products. We have the type of function, and we have the arguments. What we are looking for is actually the Frechet derivative. For this question, this is what we are asked to get and what it is. So using this relationship that we have on the table, we will see that this will be equal to d f of s ds ds. Comparing the left-hand side with the right-hand side, you will see that your df of s ds is actually your identity tensor. So when your function is a trace, This dfds is what we have here. When your function is a trace, your Frechet derivative is equal to the identity tensor. So you could see how we work backwards to be able to prove that our DDS trace of S is identity tensor. What we just used was the Gateau-Frechet relationship. Now I'm going to move to a case where our K is equal to 2. Then you'll be able to see how we apply this also for that kind of case. So everybody, at least so far, are we able to follow? Isayo, Godwin, Kenneth, I know Enola already said that it's clear. Are we able to follow? 2 people, please respond to me minimum so that I can move on to when K is equal to 2. Okay, Mujiradi, I can see you. We'll do K equal to 2, K equal to 3, and go to some other examples, just for you to understand this connection. Where's every other person now? Mujiradi is the only one that responded. Okay, so maybe I shouldn't wait to ask. Let me just move on. So let's look at the case where K equal to 2. For K equal to 2, we are supposed to show that DDS trace of S squared is equal to transpose of S. Remember the proof in that slide 11, the proof is actually that we should show that DDS trace of SK is equal to K into SK minus 1T. So you will see that when K equal to 1, if you put 1 in, if you put 1 inside this, you will see that what we have is the identity tensor. If you put K equal to 2, you will see that what we have is what we have here. So we are supposed to do this, this proof. So we'll use the same method that we used. First of all, write the Gateau differential. First of all, we'll write the Gateau differential. So the Gateau differential in this case is going to be d alpha but in this case, we have our trace S squared. So if we are going to write it based on our specific question, this will be written as d alpha trace S plus alpha delta S squared. Based on the question that we're given. Okay. Let's open up that. D alpha trace of S plus alpha ds S plus alpha ds. Alpha goes to 0. So we are going to use like a form of product rule. Okay. We'll do the differentiate the first one, keep the second one, keep the first one and differentiate the second one. If we do that, what we'll have is trace of, if we differentiate the first one with respect to alpha, you have ds, keep the second term, then keep the first term and differentiate the second term. alpha going to 0. Now apply your alpha equal to 0. When you apply your alpha equal to 0, what you have is trace of the S composed with S plus the S. No, we kept this, okay. Alpha equals to 0, composed with S ds. Okay, that's what we have. And if we are going to write this trace, if you change the positioning of the S, you know that you will get S transpose. So if we are going to write this trace, let me just finish it up in this corner. In another form, you know that this can be written as 2 transpose of S ds. So if you look at how we write our trace when we have 2 tensors, there's a proof that we say that for each of these terms here, you have S transpose dot ds plus S transpose dot ds. So it gives you 2 of it. Now, if you write this based on the table we had, if you write this based on the table we if you write this based on the table that we had, we would see that this means that the S trace of S squared is equal to 2st. So for k equal to 2, sorry, there's a 2 here. My apologies. That's the proof. I'm going to pause now. Look at the steps at the first example and the steps of the second example. Are you able to connect both to see how we're able to arrive to get this proof? I'm just waiting for us to respond. And if you have any question, please ask. Yes, anyone. So we can do the k equal to 3 that is on slide 11. And what I just want you to recognize are the steps. It's similar steps, it's just that the functions that we are giving is different. Any questions? Are we still here? Hello? Okay, Fisara says they are still here. And also, can you see that we took similar steps, like the first question, to arrive at our results? Are you talking commutative because of the arrangement of the S and the DS? I just want to be sure of where you are looking at. Are you looking at when we wrote the trace of the SS plus SDS. Is that where you're asking if there's a commutative relationship, Enola? Remember that the trace gives you, when you are finding the trace of the composition of tensors, you get a scalar. You get a scalar. When you change the positioning of your tensor in rewriting the trace in this form, we are looking at the whiteboard. If you check your notes on tensor algebra, you will see that it can be written as the transpose of one of the tensors double dot the other tensor. So you could go to tensor algebra to check that out. But we capitalize on the fact that the trace gives you a scalar result. Is that clear, Nola? Okay, I'm going to proceed. I'm not getting any feedback from you. Okay, I'm going to proceed. So let's look at when k equal to 3. So we have to show that DDS, trace of S cubed, is equal to 3S squared transpose. So remember that is trace DDS, trace of SK is equal to K into SK minus 1 transpose. So I'm just putting in the value of the K. So we have to also show this. We write the Gateau differential. When you write the Gateau differential, you can also rewrite it as this for this case. We use the same thing we did the first time, using kind of the product rule. Differentiate the first one, keep the other two. Differentiate the middle one, keep the others, like that. So this will give us trace of, if I do the first, I will have DS, keep the other two. Plus, leave the first one, differentiate the second, leave the third one. And leave the first and the second, differentiate the third. Now put in alpha equal to 0. So we have trace of ds ss plus s ds s plus ss ds. We'll write this trace in another form. You will see that this can be written as 3 s squared transpose dotted with ds. Okay, and this should be the same as your Frechet derivative dotted with the arguments. And from here, you will see that the trace, and in this case, our function is the trace of S cubed. So you will see that that proof is done. Same step, first one, second one, third one. Just a little bit of difference in the manipulation of doing the differentiation. and the results for your Frechet derivative comes out naturally. Any questions? Mujira, is this clear? Duka, Fisayo, Godwin, Kenneth, Enola. One of the things that you see in this tensor, algebra, and calculus is you have to recognize some certain patterns that you can see in solving this kind of problems. You will see that from the first one, we recognize a particular pattern in which we can write this, and we just went on and on till we got our answers. All right. So I want us to look at the tutorial slides, and we need to pick just maybe 2 more questions that apply this Frechet derivative so that we can move on to the grad and the div and the curve and solve some questions there. If you look at the slides, I want you to look at yours and pick 2 from slides 12. The same question on 12 is continued on 13. So slide 12, slide 14, slide 15, just look at it, slide 16, slide 16, have some similar questions there. I think out of the slides I just called out and slides, from the slides I just called out, please pick 1 question. Pick another question from slides 24, 25, 24 and 25. I think those are similar, they have similar questions. So I need 1 question that has to, you have to write in component form, and the other question that has to do with just writing these derivatives and doing some proofs. So I'm waiting in the chat room. Let me see the questions, 2 questions from there, so we can go on to 2 problems that have to do with the grad and the div and the curve. So I'm going to mute myself now, give you 3 minutes to look through and just post the questions you want me to solve. Up till slide, up to slide 26. Up to slide 26. From slide 27, we definitely picked some questions from there. Admin, I guess there's a student that wants to come in. Please, can you help attend to that? Anyone in the waiting room, please allow them in. So I'm just waiting for you to just pick your questions up to slide 26. We'll pick another set of questions from 27 so that we can make use of the remaining hour to. Okay, let me mute myself. I'm actually a host, but I can't see Akinola in the waiting room. So Mujira, they maybe just communicate to.
There's nobody in the waiting room. There's no waiting room.
There's nobody in the waiting room. So maybe his internet is having some problems. Just let him know. If he's there, we'll allow him in. If we don't pick any questions, I'll just go on and solve any question I want. If that's what you want me to do, it's no problem. Slide 26, okay. I picked that. Another one, 2 questions. I'm waiting for 2 questions. Okay, slide 16 and 26. So I only have Enola respond. So I guess I'll just pick his questions and solve it. Oh, 25. Okay. Let's see how we do on time with Jira Day and see whether I can do both 25 and 26. But let me first of all look at slide 16 and see what is there. Okay. Use the Cayley-Hamilton theorem to express the third invariant in terms of traces only. That's the first part. And of course, our Cayley-Hamilton theorem, if the tensor we are looking at is S, Cayley-Hamilton theorem says S cubed minus what's the invariant of S squared plus second invariant of S minus third invariant of S composed with the identity tensor is equal to 0. Please, everybody note that this I1, I2, I3 is not identity tensor. They are invariants. The first invariant is the trace of the tensor. The second invariant is the cofactor of the trace of the tensor. And the third invariant is the determinant of the tensor. So you must recognize what is the first invariant, second invariant, and the third invariant. Okay. So we are supposed to express the question. The first part of the question said, use the Cayley-Hamilton theorem to express the third invariant in terms of traces only. So we are supposed to express the third invariant of our tensor S in terms of traces only. Everything that will be on our right-hand side must just be in terms of traces, okay? So the first thing that we'll do is to take the trace of every term in this equation. So we are going to take the trace of S cubed. We'll take the, remember that the trace of S, this first invariant here is a scalar. And you cannot take the trace of a scalar. So you will take the trace of S squared. The second invariant, you cannot, it's also a scalar. You can't take the trace of a scalar. So you take the trace of S. And of course, you will take the trace of the identity tensor. So taking the trace of all the terms, we are going to have the trace is the first invariant. So first invariant of S cubed minus, you write this first invariant because you can't take the trace of that. Then you now take the trace, which is the first invariant of S squared, plus, you can't take a trace of this because it's a scalar. So you take your trace, which is the first invariant of S, and you can't take a trace of this because it is your determinant, is a scalar, and you take the trace of your identity tensor equal to 0. Okay? So, and this you can also rewrite. You can also rewrite by taking every other thing to the other side and writing this as first invariant of is equal to and we know that the trace of the identity tensor is 3. The trace of the identity tensor is 3. So that would be 3. So we have rewritten that. Okay. Now you know that your second invariant can also be written in terms of traces. Your second invariant can also be written in terms of traces. So you will see that you can also rewrite what you have there as first invariant of S this second invariant, you know, is the same as first invariant squared of S minus first invariant of S squared. Half of that is your second invariant. If you have read if we read our notes very well, I think it was stated somewhere. Let me just get that out so that I'm not confusing anyone. Let me just confirm that that is correct. Yes, it is. I think all of us should be able to confirm that the second invariant is the first invariant squared of S minus the first invariant of S squared. Can you check that? Is that correct? I think it should be. So that's I2S, and it will be multiplied by I1S plus 3 third invariant of S equal to 0. So let's look at the terms. This term here is this one here. The second invariant here is the whole of this. They're multiplied by that. And this is the 3, the third invariant is equal to 0. Okay. Has anyone confirmed the expression I wrote for that second invariant? Is that correct? I don't want us to just be writing. I want us to also check. The trace of the cofactor. It has been okay. All right. Thank you. So the next step that we'll now do, the next step now is that we are going to open up that bracket. You will see that you have some common terms here. So let me put this in brackets. So if we open that up, we'll have I1S squared. Open up this bracket. I think the first thing that we need to do in this case is to multiply throughout by 2 so that we don't have that half there. Are we all following what I'm doing? So that I'm not speaking to myself. I know Enola is here with me, Mujirade and every other person. Are you following the steps from the Cayley-Hamilton theorem? Okay, so I don't want to see that half. So what I'm going to do is that I'm going to multiply throughout by 2. So let me do that step first before I open the bracket. So I will have 2 first invariants. Okay, so just check that. I'll need to clean the top of the board so that we can keep going. So what I did was just multiply throughout by 2, and this is what I have. And if you look carefully, you see that you can add this term and this term. If you look carefully, you see that we can add those 2 terms. Okay, because we have first invariant of S, first invariant of S squared common there. Should I give you a minute or should I go ahead? Should I move on? And here also you see that this is first invariant squared of S and first invariant of S. So this will give you first invariant cube of S, okay? So let me clean the top and leave the last expression. If you check your slides, you see that some of the steps were skipped. So what I'm just doing is just to ensure that we get the whole thing. Most especially Enola that chose this question. I hope it's getting clear to you how this was done. Okay, so from this last expression, you see this is where we are coming from. From this last expression, we'll now have 2 first invariant of S cubed. The first and the second to the last term can be added together because there are similar terms there. First invariant of S, first invariant of S squared. The second term is similar because we have trace squared and we have trace. That will give you trace cube. So this will give us first invariant cube of S. That's what we have there. Then the last term. Or you remember that the question was asking us to write the third invariant in terms of traces only. It means that our third invariant needs to be on one side and every other thing will be in terms of traces. We already have it, but if we write it out, it means we'll have 6 third invariant of S will be equal to will be equal to 3 first invariant of S. No. 2 first invariant of S cubed minus 3 first invariant of S first invariant of S squared plus first invariant cube of S. So when we divide through by 6, dividing through by 6, you will get the answer in that slide. They just rearrange the terms. So let me just write exactly the way it appears there. 2 first invariants of S cube plus first invariant cube of S minus 3 first invariant of S first invariant of S squared. Okay, so let me see if we have anything in the chats. If there's any question. look at the second term. Okay. The second term of which step? Is it where we started from? Mojirade, can you point me to it? This is step 1, step 2, step 3, and step 4. So Mojirade, where do you want me to take a look at the second term? Oh, okay. Okay, Mojirade, are you good? Just respond if it has been sorted. Let me just know. Okay, great. So that's it. That's it. So we'll move quickly to, I'll just give you a minute to write the steps because I know there are some steps missing here. Slide 25. Yes, 25. Okay. So I'm moving on to, I'm moving on to slide 25. Can I go? I want us to do 25 and 26, then we'll move on to the grad and the call. Your integral theorems, basically what you need is a mathematical for that. You don't need to cram anything there. Once you type in the integral theorem in mathematical, it should give you your response. So what you just need to do is go through the tutorials of the mathematical for the integral theorems and be fine. Please, can I go on? I'm looking at time. I want us to take as many questions as possible today. The self-test will be open till Tuesday next week so that we can have some time to. Wednesday, I'll be on campus physically for lectures because now that we start Continuum Mechanics proper. So I'm going to be in class on Wednesday. So I want us to use the June 12th period to ensure that we are done with the self-test into Tuesday. Hey, everybody, should I go on? I think I'm more concerned about doing more questions than you are. The time we are taking is really a lot.